Before we do start in on division, I just want to say digesting those alternative algorithms can feel a little haphazard given that we had to go relatively quickly today. The questions you're going to be asked about those will basically be, can you tell them apart? Do you know which one's which? So you're not going to be asked to do a whole lot of performing calculations with the Egyptian duplicity method. I want you to know it exists. I want you to know how it works. But if you can identify which one's which, then you should be in pretty good shape with those. You'll see some practice in the homework, but when you get to the quiz, it's more about just realizing they exist and being able to tell them apart from each other. All right, let's talk division. Starting with division the same way we started with the others, with commutative associative identity. These will be relatively quick. 6 divided by 3 equal to 3 divided by 6. 6 divided by 3 is 2. 3 divided by 6 is 0.5. Nope. We do not have a commutative property of division. We can't divide in any order we want. Associative. If I wanted to do, say, 10 divided by 5 divided by 2, and see if that was equal to 10 divided by 5 divided by 2. Boy, I don't know. I'm a little skeptical. I don't think it's true, but let's see. 10 divided by 5 would be 2. Divided by 2 would be 1. On the other side, parentheses first, so 10 divided by 5 divided by 2 is 2.5. 10 divided by 2.5, that would be 4. So that doesn't work. So no, we do not have an associative property for division. Nope. Identity, as you probably would have guessed, if we do 5 divided by 1, we get 5. Well, that looks good. There's a number I can divide by and get the same value back. But remember, identity has to work both directions. And if I do 1 divided by 5, I don't get 5. So there is no identity property for division. So commutative associative identity, they work for adding and multiplying. They do not work for subtraction and division. Division with 0 is a really important idea. If we want to do 0 divided by 4, that's perfectly fine. We get an answer of 0. The idea here is that we have nothing, and when we want to divide that nothing into 4 equal piles. Okay, no problem. Each pile gets nothing. No problem there. I have nothing, and I put it in 4 equal piles of nothing. In contrast to this, if we try to do 4 divided by 0, this one is undefined. And the reason here is we have 4 things. We want to put those into 0 piles. Well, that doesn't even make any sense. I can't take 4 things and put them equally into 0 piles. So dividing by 0 is not allowed. Dividing by 0 is undefined. It's okay to do 0 divided by a number. That's okay. We just get 0 as an answer. But it's not okay to divide by 0. That's undefined. Doesn't make any sense. Quick poll for you. True or false, the set of natural numbers is closed under division. I'll make a poll for this one. True or false, the set of natural numbers is closed under division. Meaning, if I have a natural number and I divide by a natural number, is my answer a natural number? We did great with closure for multiplication, so I feel pretty good about how we're going to do here too. We'll go another 20 seconds and then we'll talk about it. All right, let's see how we did here. Not unanimous, but really strong agreement. Okay, that's very good. So remember, anytime we're answering a true false question in mathematics, it has to be true every single time, no exceptions. So if I can find one place where this natural numbers is not closed, then it's false. And if I try to do 2 divided by 3, that's a natural number divided by a natural number, my result is not a natural number. So right there is all I need to say false. Is it possible to do 2 natural numbers and get a natural number as an answer? Sure. But in order for us to say it's true, it has to happen every single time, no exceptions. As soon as we get this exception, we can say it's false. Just like our other operations, we do have a standard algorithm for division. And if I want to do 825 divided by 5, we set up this thing to do long division. We set up this scaffolding here to do 5 going into 825. And our approach here is to not look at 5 into 825, it's to look at 5 going into that 8 right there. And 5 will go into 8 one time, and 1 times 5 is 5. When we write that down, though, we're taking place value into account here, because what we're really saying is 5 going into 800, and the reason we put that 1 up there is because it will go in 100 times. So our place values get taken care of for us by this algorithm. It's kind of beautiful that way, kind of like the lattice method takes care of our place value positions for us. Using this scaffolding here for long division takes care of our place values for us. And then we subtract to see what we have left. And we do 8 minus 5, and that's 3. Keeping in mind what's happening in the background here is 5 went into 800 100 times, and there's 300 left over. They're in the right place values because of this structure that we use. Okay, then we bring these two 10s down and say 5 going into 32. Well, that'll go in there 6 times. 6 times 5 is 30. And we'll subtract and see what we have left, and that's 2. Bring that 5 down. 5 will go into 25 5 times. 5 times 5 is 25. We subtract. We don't have a remainder. And so 825 divided by 5 is 165. Essentially, what that's saying is if you had 825 things and you wanted to put them into 5 equally sized piles, each pile would have 165 things in it. That's our standard algorithm for division, and it takes care of our place value positions for us. That's part of the beauty of it. Base 10 blocks are a manipulative that you might be able to work with in the classroom. I kind of hope so. The idea here is this thing is a 1, and we call it a cube. This thing is a 10. It's 10 ones strung together, and we call that a long. And this thing is a 100. It's 10 by 10, and we call that a flat. So base 10 blocks are really great for working with different numbers, and we call those cubes, longs, and flats, and they represent ones, tens, and hundreds. One of the things you can do with base 10 blocks is you can do division before you've ever learned the standard algorithm. And here's what I mean by that. If we want to do 432 divided by 3, and we're not going to use the standard algorithm. Maybe we haven't even learned that yet. We're just getting the idea of division across. 432 divided by 3, and we have the 432 as 4 flats, 3 longs, 2 cubes. And when we divide by 3, we want to put these in 3 equal piles. So I'm going to make my 3 equal piles over here. This won't be a work of art, I promise you. There's my 3 equal piles. And I'm just going to start putting stuff in them. So I'm going to take one of these flats and put it in each one of those. So I put a flat in each one. Okay, now I have 1 flat left. And unfortunately, I can't take that 1 flat and put it into 3. What do you think I would do here? What do I need to do? Keeping in mind I have a full classroom set of base 10 blocks. what do I need to do with that flat before I can start putting it into those little piles that I have drawn? Excellent, Stephen. You're exactly right. I'm going to take this flat and I'm going to turn it into 10 longs. And now I'm going to take my longs, good, Katrina, and then put those in the piles. And let's see. So, well, what do I have? I have 5, 10, I have 13 of those. You could just do it one at a time and say, one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh, I have one long. There's nothing I can do with that. So what I'm going to have to do with that one remaining long that I have is turn that into 10 cubes. And then I can start putting my cubes in. 1, 2, 3, 4, 5, 6, 7, 8, 9. Better figure out how many I had. I had 12. 10, 11, 12. And now I can look at my piles and see, well, what's in each pile? Well, I have 144. And that's the same in every pile. And so I just did 432 divided by 3 using base 10 blocks to find out that that must be 144. It's a way to sort of do division without having the standard algorithm yet. And it's a great thing to do before learning the standard algorithms. Then you go, well, this is great, but we also have this other approach we could use to divide 432 divided by 3 and see how that plays out. Make sure you know the cube, long, and flat. You might be asked to identify those at some point. Estimation with division. There's a couple of different techniques. One of those is rounding up, turn it into something that's easier to deal with. Again, remember, we're estimating. I know all of us really like a single right answer. With an estimate, we're just looking for a ballpark. I just want this to be something I could do in my head. So if I round this up to 500 and I round that up to 20, now I have 500 divided by 20. Hey, this is kind of like what we did with multiplication. 500 divided by 20, I could change that. Or I could say, wait a minute, I can divide this one by 10 and make it 50. If I divide that number by 10, I can also, well, I don't want to say it this way because it's not like the multiplication. Sorry about that. 500 divided by 20. So if I have 500 divided by 20, I can create an equivalent fraction here. I can divide the top by 10, divide the bottom by 10, and now I can do it in my head. Sorry about this. This isn't like the multiplication ones. It's a little different because we're estimating. Compatible numbers. What compatible numbers are is you try to make this into something that looks like it'd be easy to do. 4,132 divided by 7, I don't know. But what I can do is I know 7 times 6 is 42. So if I could turn this into 4,200, that's a number that's really compatible with 7. And this I could do in my head because I know 7 will go into 42 6 times, and so my answer is 600. Again, we're estimating. We're coming up with a ballpark. We want something we can do quickly and easily. And so if we round these up to numbers that are easier to work with, if we turn this into a number that's easier to work with for this particular problem, if that wasn't divided by 7, then I wouldn't use 4,200. I'd want to use something different. If it was divided by 5, then I might use 4,000 instead. But I just want to make it into something that's easier to work with than what I've been given for an estimate. Missing digits problems can be kind of fun. They're like puzzles to solve. There is a certain amount of trial and error involved in here, but we can have a strategy. And the strategy I want to share with you is taking a close hard look at the ones digits. Because if I'm given this problem, 4 blank blank 2 divided by 8 blank equals 48, and I want to figure out what numbers go in those blanks, I don't want to do this blindly. what I want to do is look at the ones digits, because that's going to help me figure out what goes in this spot right here. Because if I just look at the ones digits, I've got 8 times something has to result in a 2 in the ones place in my answer. So if I do 8 times something that has to result in a 2 in the ones place, what could that something be? What single digit could go there? What ends up with a 2 in the ones place? 4 does. Good, Austin. If I put a 4 in there, 8 times 4 is 32. Sure enough, that works. Katrina says 4 also. That's right. 8 times 4 gives me 32. That gives me a 2 in the ones place, so that works. Let's see how this plays out in this problem. So if I drop a 4 in there and I do 48 times 84, I get 4,032. 4032 divided by 84 equals 48. Sure enough, that worked. I filled in those blanks. I didn't do it blindly. I didn't just randomly start throwing stuff in there. What I did was I took a look at the ones digit as a strategy. One of the things that's kind of wild about this one, though, is, well, 8 times 1 would be 8, 2 is 16, 3 is 24, 4 is 32, 5 is 40, 6 is 48, 7 is 56, 8 is 64. 8 times 9, though, is 72. So this could be a 9. What if I try a 9 in there then? What if instead of a 4, we put a 9 in there? And so let's see if I have 48 times that 89, that's 4,272 divided by 89 equals 48. Just happens to turn out to be 2 different ways to get a correct answer here. Trial and error helped us get an answer, and turns out there's 2 answers that work. If there's ever a problem like that, you get credit for either one. You wouldn't have to give both. I just want you to see that sometimes there's more than one way to land on a correct answer on these missing digits type of questions. And just in case I went too fast, and again, this is just trying to make sure I get us done in the next 18 minutes. But once I knew that a 4 was going to work here, essentially what we're saying is this 4 blank blank 2 divided by 84 equals 48. What I did then was get rid of this 84 by multiplying by 84 on the left, multiply by 84 on the right. Those cancel, and then 48 times 84 helps me fill in those 2 spots. So that's how we got that. Sorry for glossing over that again. It's just trying to make sure we get through everything I need to. Here's a problem that I'm just going to throw at you and let you do a poll with it. Amy is making bracelets, and each bracelet uses 3 red beads and 7 yellow beads. She has a package of 25 red beads and a package of 45 yellow beads. How many bracelets can she make? I'll make a poll for this and let you try it. And the idea here is, how many complete bracelets can she make? If you get an answer that's not there, it's okay to pick the one closest to yours, and then when we talk about it, you can ask about it. And this one takes a minute to understand what's happening. When she makes a bracelet, it's got 3 reds and 7 yellows in it. We know how many reds, we know how many yellows. How many bracelets will that let her make? Let's go another 15 seconds, and then we'll talk about this one. All right, let's see how we did here. Strong agreement, not unanimous. All right, let's take a look here. So basically what we're after here in the top of this page is a little bit of a hint where it says limitations, because it lets us know that it's the limitations we care about. And as far as the red beads go, well, she has 25, and every bracelet she makes, she's going to use 3. So she could make 8 bracelets with the red beads that she has. But then with the yellow beads, she has a package of 45, but it takes 7 to make a bracelet. So when we divide 45 by 7, that's going to give us 6 point something. She could make 6 complete bracelets with that. Well, it's great that she could make 8 with the reds, but she's going to run out of yellows first. And so 6 is the number of bracelets she can make, because the yellows is what she's going to run out of first. That's the key there, is yellows run out before the reds do. So the number of bracelets she can make with the yellows is the number she can make. Another one for you to just try. Amy is selling those bracelets. She has 24 bracelets that she plans to sell for 70 cents each. Unfortunately, 2 of them broke before she started selling them. In order to bring in the same amount of money as if the bracelets wouldn't have broken, how much should she charge for each of the remaining bracelets? A key here to this one is that I want you to answer in cents, not dollars, and then round your answer to the nearest whole number. I'll make a poll for this one and let you try it. A little bit of problem solving skills all the way back to the very first week of the semester rolled into this one. I don't think it's a problem that's overly difficult as far as understanding the structure of it. Solving it uh, can be. There's a couple of hurdles in here that I want to make sure I have a chance to talk with you about, because while I think you probably understand what to do and how to do it, making sure that you report the answer the way it's asked for is a key part of this one. Let's go another 20 seconds and then we'll talk about it. If you need more time, let me know. If you get an answer that's not there, pick the one closest to yours. All right, let's see how this one went. Okay, some agreement, but we're really spread around on this one. All right, we better be really patient and careful as we go through this one. You let me know if you have questions about any of the things we discussed here in this one. So she started out with 24 bracelets that she wanted to sell for 70 cents each. 2 of them broke, so she's only going to have 22 to sell. But originally, at the start of this, what she was hoping to do was 24 bracelets times 70 cents. So 24 times 70 is 1,680 cents is what she was going to make. Now, this says answer in cents. So I'm going to work the whole problem in cents. I'm not going to work it in dollars. I'm going to work it in cents because it says answer in cents. So 1,680 cents. Unfortunately, she only has 22 bracelets because 2 of them broke. So we'll divide that by 22 to figure out how much she's going to have to sell them for. And when I do that, I get 76.363636. At the end of this, it says round to the nearest whole number. And so if I want to round this to the nearest whole number, I'll look in the ones place. That's 4 or lower, so we'll round this down to 76. And she's going to have to sell them for 76 cents. A couple of things about the answer choices in this question. They're intentional. If you say, but she's going to have to do 77 cents because if she sells 22 bracelets at 76 cents each, that's 1,672 cents, and she was supposed to make 1,680. You're not wrong that technically she would need to sell 77. This is one of those limitations we have working in Canvas. When we work in Canvas, we're restricted to how Canvas can round sometimes. And what Canvas can do for us is round to the nearest whole number. So if the instructions say round to the nearest whole number, then that's what we're going to do. And we're going to go 76. And we're going to say that 1,672 cents close enough. She made the same amount of money if we're rounding to the nearest whole number for pricing those bracelets. Another answer here is if you do this in dollars and you say 24 times 70.7 dollars, and then you get $16.80 and you divide and you get 0.76. This answer is in dollars. It's $0.76. We want to answer in cents, not dollars. The idea that the answer is in cents, well, 0.76 cents, that's less than a penny. That doesn't make any sense. We want to throw that out. And so an answer of 0.76, I understand where it came from and how you got it, but because we're told to answer in cents, not dollars, we definitely don't want to answer with 0.76 because 0.76 cents is less than 1 penny and wouldn't make sense here. So my guess is most of you are really comfortable with that problem. If you said 77, I totally understand why. We're going to round to the nearest whole number. If you said 0.76, your answer was in terms of dollars instead of cents. Just leave it in terms of cents and you'll be just fine. Value of the quotient type of problem. If you divide a number that's larger by 90 by a positive number that's less than 3, what can you tell about the relative value of the quotient? Whew, that's a mouthful. All right, let's streamline this a little bit. So we're going to divide a number that's larger than 90. So something that's larger than 90, we're going to divide that by a number that is less than 3. So we're going to have something bigger than 90 divided by something that's less than 3. What can you tell about the relative value of the quotient? The quotient is just the answer to a division problem. So that one, the mystery's gone. And then relative value means what can you say about the answer to this question? We can't necessarily say that it's going to be 9 or anything like that because we could have anything here. Something bigger than 90. I don't know. What about 92? Something smaller than 3. How about 2? If we divide those, we get 46. Well, 46 doesn't feel like the answer here, and you're right, it wouldn't be. That's an example, though. It lets us understand what's going on in the problem. Something bigger than 90, something smaller than 3. Okay, but what if I pick something bigger than 90 and something smaller than 3 that were really close to 90 and really close to 3? If I do 90.1 divided by 2.9, now I get 31.068, and it keeps going. Okay, so my answer can't be 46, and it's probably not 31. What happens here is this. We're going to approach this problem from a standpoint of saying, what if I pick something that is really close to 90, and I pick something that is really close to 3? Essentially, what I'm doing here is really just doing 90 divided by 3 would give me 30, except for the fact that the number on top has to be a little bigger and the number on the bottom has to be a little smaller. What that's going to do, that's going to make my quotient bigger than this number right here. So what I can say about the relative value of the quotient is that it has to be greater than 30. Our approach here is to say, all right, I'm just going to pretend that it really is 90 divided by 3. That would be 30. That's my baseline. Now, okay, if the number on top gets bigger and the number on the bottom gets smaller, then the answer to this problem is going to be bigger than 30. And then that's what I'm going to say for my result here, relative value of the quotient. I want you to try one like this. If you divide a number smaller than 28 by a number greater than 7, what can you tell about the relative value of the quotient? I'll make a poll for this one. I don't think these are easy, but I do think they're not easy right off the bat, but you tend to get the hang of them really quickly once you get the hang of them. So a little bit of practice goes a long way with these. And putting in some real numbers can be really helpful here. Putting in some actual numbers can really help you get to the answer. I know we're getting close to the end of our class time. I do have just one more thing to talk about after we resolve this one. And then we will have fit 4.1 and 4.2 in there today. Not quite as elegant as I was hoping, but we're going to get it in there, so that's all right. We'll go another 30 seconds on this one, and then we'll talk about it. I think when you first read a question like this, it can really spin you around a little bit. But once you understand what it's asking for, it's not so bad. Let's see how we did on this. Okay, there's some agreement here, but a little bit of disagreement. It's either greater than or less than, so that's kind of good news. We're one of those, which are the two best options. All right, so here, a number smaller than 28 by a number greater than 7. First thing I'm going to do is just pretend it's 28 and 7. That would be 4. So this is going to have something to do with 4. And now what I'm going to do is I'm going to make my top number smaller and my bottom number bigger. Okay, well, how about I make it 20 and 10. That would be 2. Oh, well, that's less than 4. So that means every time I do this, my relative value of the quotient must be less than 4. I just need one example to kind of push me in the direction of less than or greater than. Last thing I want to say today before we close, just some notes about your homework. When you see the term break even in a problem, what that means is there's no profit, no loss. It's just zero. Nothing was gained, nothing was lost.